resistance or R&R circuit. So first is a coil of wire possesses properties of resistance and reductance that are interdependent, therefore called an impedance coil. The next is to determine the resistance and inductance of the coil. It is sometimes desirable to connect a fixed resistance in series to the unit, then measure the voltages EZ, ER, and E and the current I. Next, let's go to the circuit diagram of RLR circuit. So this is the diagram. Resistor and inductor. So this is the impedance coil. Then it is stated earlier that to determine the resistance and inductance of the coil, it is sometimes desirable to connect a fixed resistance. So here, let's connect a resistor in series. So, next is, from here to here, we can identify the EZ or voltage of the impedance coil. Then from here to here, we can determine the ER or the voltage of the series resistor. And then from here to here, we can determine the overall resistance. So next step, let's convert the circuit diagram into a phasor diagram. So first is let's draw a horizontal line, which is our reference phasor, and let's label it I. So next is draw a phasor ER, so here, and then in phase, so align siya sa I. So next, let's draw an arc upward. Label it EZ. So next is swing another radius, intersect with the region O. So kani siya. So next is kung itaon nila to siyang angle. Since kani siya, siya yung measurement, tana siya kani. Ang ato na pagitaon kani siya nga side o kani siya nga side. Para mapangitan na nato siya, natay given nga EZ, which is the hypotenuse and our adjacent. So, ang iyahang equation is EZ cosine theta. Then, kanisad siya, opposite of hypotenuse. So, ang atong gamiton EZ sine theta. Then, this is our new triangle kani. Triangle A ay triangle O, AB. Expression of triangle OAB. So, this one is the side A, side B, and side C. By Pythagorean theorem, E squared is equal to ER plus quantity ER plus EZ cosine squared plus EZ sine theta squared. So, simplify. E squared is equal to ER squared plus 2ER EZ cosine theta plus EZ squared theta plus EZ squared sine squared theta. After out, this one so ER squared plus 2 EZ cosine theta plus EZ squared cosine squared theta plus theta. So this one has an identity cosine squared theta is equal to 1. Simplify, E squared is equal to squared plus 2R sine theta plus squared. So transpose this one, and divide it by this one. E squared minus ER squared minus EZ squared all over 2 ER EZ is equal to cosine theta. coil by using the equations R coil is equal to EZ cosine theta over I, and the inductance of the coil is equal to EZ sine theta all over I times 2 pi f. So let's have an example. So first is a 115 volt 60 cycle source is connected to a series circuit consisting of a fixed resistor and an impedance coil. If the resistor and the coil voltage drops are 55.4 and 80 volts respectively, under which condition the current is 1.69 amperes. Calculate the resistance and inductance of the impedance coil. So here are given E is equal to 115 volts, ER is equal to 55.4 volts, EZ is equal to 80 volts, and I is equal to 1.69 amperes. Let's find the resistance of the coil and the inductance of the coil. So let's find sine theta. To find sine theta, use the first equation. The equation cosine theta is equal to E squared minus ER squared minus EZ squared all over 2 ER Z. So E squared 115 minus 55.4 minus 80 squared all over 2 times ER 5.4 times 80. This is equal to 3,755 over 8,865, which is equal to 0.423. This is cosine theta. So theta is R cos this one. So theta is equal to 65 degrees. Sin theta is 0.423 over I, which is 1.69. So R coil is equal to 3 ohms. Third B, inductance of the coil is equal to EZ sine theta all over I times 2 pi f. So the value of 2 pi f is equal to 377. So EZ, which is 80 times sine of theta 0.906 all over I, which is 1.69 times 377. So N coil is equal to 0.114 Engr. So 2 pi f here is equal to 377 because our source is a 60 cycle. So substitute the 60 cycle is our frequency. So substitute 2 times 3.14 times 60 is equal to 377. Let's have our example number 2. So, an 8 ohm resistor is connected in series with an inductive coil, and the combination is connected across a 120 volts 60 Hz source. A voltmeter connected across the resistor reads 32 volts and 104 volts when connected across the coil. Determine the resistance of the coil. So here are our given. Resistance is 8 ohms with a voltage across the resistor 32 volts and total voltage of 120 volts, frequency of 60 hertz, and voltage across the coil is 104 volts. So find the resistance of the coil. To find our coil, first let's find the current. For A, I is equal to the voltage across the resistor over the resistance. So ER is 32 volts over the A. So current is equal to 4 amperes. Let's find the impedance across the coil. So Z coil is equal to the voltage across the coil over the current. So voltage across the coil is 104 volts over the current 4 and is equal to 26 ohms. So next is let's have the equation Z coil squared is equal to R coil plus XL squared. Substitute 26 ohms to Z coil, so 26 squared is equal to R coil squared plus XL squared. Therefore, transpose this to here, so XL squared is equal to 26 squared minus R coil squared. This is our equation 1. Finding equation 2, so let's have ready. Total impedance is equal to the total voltage over I. Total voltage is 120 volts over current 4. We have the total impedance of 30 ohms. Z total squared is equal to 8 plus squared plus ZT is equal to 30, so 30 squared is equal to 8 plus R coil squared plus XL. So this is our equation 2. Next is substitute equation 1 to equation 2. Substitute equation 1 to equation 2. So 30 squared is equal to 8 plus R coil squared plus 26 squared minus R coil squared. Isolating R coil, so R coil is equal to 10 ohms. Total impedance in series is equal to Z1 plus Z2 plus Z3 and so on, while total impedance in parallel is equal to 1 all over 1 over Z1 plus 1 over Z2 plus.
Hello again, ladies and gentlefolk. It's time to discuss a new concept in LCR circuits, although in retrospect, you should realize that it's not a new idea at all. What I'd like to go over is this thing called impedance. We know that an LCR circuit contains a resistor, a capacitor, and an inductor. In previous modules we looked at each of these components in detail and perhaps you noticed what they all have in common. All the components in the circuit have some slowing effect on the electricity that flows through them. They all show some kind of opposition to the current provided by the power source. You see, a resistor is designed specifically to limit the current in a circuit. It resists, it's in the name. A capacitor collects charge from the circuit in a way that makes it very hard for current to flow through it. Remember, a capacitor consists of two conducting surfaces that are separated either by air or by a dielectric layer. And an inductor, according to the laws of Lenz and Faraday, opposes any change in the amount of current through it. This you should be familiar with by now. So if you take each of these components and plug them into a source of alternating current, as I've done here, they all oppose or impede the current. Current flows into the resistor says, "Not so fast there," and it acts a bit like a toll booth. Then current tries to go through the capacitor, but the capacitor says, "No, you ain't going nowhere," and it starts to charge up. Because we use AC, the size of the current is changing all the time. That creates a changing magnetic flux in the inductor, which induces a countercurrent. All these opposing effects contribute to the impedance of the circuit. Impedance is found by taking the resistance of the resistor and adding it to the reactances of the capacitor and the inductor. But it's not as simple as adding three numbers and pushing the equals button. This is the phasor diagram showing those three quantities. Notice they all point in different directions and do not line up. In fact, each reactance phasor is at right angles to the resistance phasor. Therefore, we have to use vector addition to add them all up. If you have never seen vectors before in your life, I suggest you pause this video right now and go over to the mechanics section. Phasors are defined as vectors which rotate, so their directions are important. Luckily, finding the impedance becomes very straightforward once you understand how to add these phasors up. First, we can subtract one reactance from the other. This is because the inductor and capacitor have reactances with the opposite phase. They are exactly 180 degrees apart. So take the smaller one away from the bigger one to get a new vector, the net reactance, if you will. Now, the reactance is at right angles to the resistance phasor, so we have two sides of a right-angled triangle. That impedance we're looking for is the third side of the triangle. What do we do with right-angled triangles, folks? We use the theorem of Pythagoras. Now you take your calculator out and use this fantastic formula. I'll run through a quick demonstration so you can see the whole process. Suppose our capacitor has a reactance of 10 ohms, and our inductor a reactance of 6 ohms. The resistor is a pretty skinny one, rated at 5 ohms. Here's what it looks like when we plot that data on the phasor diagram. The capacitor has a larger reactance than the inductor, so we take the smaller one away from the larger and get this. Now we have two sides of a right-angled triangle, and the impedance is the hypotenuse. I'm going to use the Pythagoras theorem, and I'd like you to watch the working steps closely. And the answer comes out as 6.4. Impedance is still measured in ohms, so that is 6.4 ohms for this particular LCR circuit. Good show! To recap, impedance is the total opposition to the flow of electric current in an LCR circuit. It is found by taking the vector sum of all the resistances and reactances that can be measured. In our equations we give it the symbol Z and measure it in ohms. That is all you need to know for the next series of exercises. I thank you for your attention.